Hello, guys. Today, I've got an awesome guest for this interview. It's unbelievable that he took the time and is going to answer a few of my questions. It's Professor Larry Wasserman. He's a well-renowned statistician. He knows so much. His work is well-renowned. He's won awards. He's going to tell us a bit about. I'm gonna be honest, you guys, just like me, we are not the best in mathematics, not the best in statistician, but the world is going to revolve around it. Machine learning, AI, computer technology, all of that has the foundation and the roots in these kind of disciplines. So I'm very, very happy that Professor Wasserman is here and will help us to get a bit of a better understanding for all of these topics and the profound foundations that allowed humans to even get to that point. Professor Wasserman, please, would you be so kind to tell our audience a bit about yourself, who you are and what you're doing?
Sure. Thanks for the nice introduction. I'm a professor of statistics at Carnegie Mellon University in Pittsburgh. I have also have an appointment in the machine learning department here at Carnegie Mellon. I've been at CMU for 36 years now. So I've been doing statistics for a long time. And yeah, that's the quick summary.
Okay, then I tend to like to get a bit of knowledge about the person. Like, how did you get into that field? Like, I'm curious, like, not that many 5 or 6 years old when you ask them what do you want to do are like, I want to go into statistics and machine learning. So how was your trajectory in your life trajectory to reach that point, if I may ask?
Yeah, it's absolutely correct that kids will want to grow up and be an astronaut or a doctor or something, but you never hear a kid say, I want to grow up and be a statistician. In fact, most people don't even know what the field is. In my case, I went to university with the intent of studying this new field, relatively new field known as computer science. But back in those days, computers were pretty primitive. There was only mainframes, and my first computer science course involved standing in a line until there was a opening at a key punch machine, and then I would sit down with cards, and you would punch your cards, and then you'd stand in line at this card reader and put that in, and then you'd get a printout, and you'd see you made a mistake in your program, and you had to go back in line for a key punch machine, and it was quite unpleasant, and it just didn't seem very interesting or exciting. It just seemed tedious to me. So I thought, well, I got to look around and find something else to do. And I took a mathematical statistics course and really enjoyed it. And so next thing I started taking more and more statistics courses, and I ended up majoring in statistics. And so I kind of stumbled into it accidentally. And I think that's sort of the story that most people who end up in statistics, at least in the olden days, that's how they ended up being in statistics, was by some sort of accident.
Really interesting, really interesting. I mean, for the viewers, it's like so hard to grasp even the theory behind it, what it was like as being a student in computer science back then. Like, you wrote out your code in paper, you only had a specified time to even be allowed to type that stuff into the machine to hopefully get a result. So I recently had an interview with Moshe Vardi. That's why he told me all about his history, how all of that was. It was like, but it also made you guys be better at programming because you had to look at the script beforehand to understand better what was going on in the machine to get the right result, compared to programmers nowadays where you do the program, okay, not working, semantic error, there's an error, and we can do it again and again and again and again. So it's really respectable how it developed back then.
Yeah,
So,
you had to be really careful because, like I say, making one mistake was, very, very time consuming. And so you did have to be kind of very careful about your program.
really, really. And so you stumbled into the field of statistics. What was it like being there at the beginning? Like, hot shot in the new field? Was there anything specific you enjoyed a lot, or was it just roaming around? How can I imagine it?
Well, it is actually an old field because, I would say it started in the early 1900s. before computers existed. But yeah, I sort of became fascinated by the fact that some of my classes were very theoretical, but some of the classes were very, very practical. And so I really found this dichotomy quite interesting, that you could do very theoretical things, but also ultimately what you were developing were tools for people to analyze data, and which is obviously very practical. And that really grabbed me. I found that to be very satisfying, very interesting. And so that's really, in fact, has been sort of how my whole career has worked, in the sense that I've always done a mixture of theoretical statistics and applied statistics. And that is the thing that I find very, very interesting about statistics, is that you can work on theory, which is lots of fun, but ultimately it's very pleasing to actually then come up with methods that you can actually implement and people can use to analyze data.
And really cool. I mean, your papers are well cited, well known. For the people who don't know, you can look it up. Google the name. All of Statistics, a concise course in statistical inference. I'm still not able, I gotta admit it myself, to properly get into the field. I'm just lacking something, but I know it's a really, really, really important field. How and when in your personal journey did you realize just how much impact it would have? Like with the computer and the statistics, was it visible from the first day for you, or was it like, no, you were as surprised as many others to see it evolve like that and to become all encompassing as it is nowadays?
Well, I always recognized that how important statistics was, because as soon as you get into it, um, you just see it being used everywhere. And when I was a graduate student, I earned money by working in our consulting lab, and you could do as much consulting as you wanted to. I mean, there was people, just lots and lots of people needed statistical consulting, but it was still a pretty, I would say, a small, relatively unknown field for quite a while, until machine learning came along. And I think when machine learning kind of started, I think it was started off as a separate field, and I think a lot of people doing machine learning didn't even know about statistics. But then eventually this awareness developed that effectively they were doing statistics. And when they became aware of statistics and started to embrace it, and the two fields started to kind of work together, then of course statistics took off. And it's these days people tend to refer to statistics as data science, or I guess data science is a broader term, but statistics is sort of the foundational element in data science. So now it's become this very, very big thing. Stats departments have gotten very popular, very big, and a lot more people obviously know about statistics, and the number of people who apply to, say, graduate programs in statistics has skyrocketed. So I think it was really when computing became much, much more powerful, and people in computer science started to do machine learning. That's when statistics, I think, really, really took off.
What would you say, when was it? 80s, 90s, early 2000s, the 10s, the 20s? I mean, 20 a bit longer.
Yeah, I always have
When
a
was the
very
spike? When did it start to skyrocket?
Yeah, I have a very bad memory for dates, but I would, because I'm trying to remember. So at CMU, for example,
Yep.
we the way it happened at CMU was we first formed a center called the Center for Automated Learning and Discovery. This was, I'm trying to remember the year. I'm going to say it was about 25 or 30 years ago. I don't remember exactly. It was my colleague Tom Mitchell in computer science who had this idea that there was this new thing happening in computer science, and he actually approached my late colleague Steve Feinberg, and the two of them were the ones who started this center, which I then became involved in. It was just a small group of us from statistics and computer science, and that eventually grew into became the machine learning department. And this was reflecting what was going on all around the world. That it was CMU was kind of a hotspot for this, but it was happening everywhere. But I would say, yeah, 25, 30 years ago is when that kind of started, and it just gradually took off.
Okay, cool. Well, for the normal citizen, it's only started now in the last few years to really get interesting because the commercial viability and all of these little trinklets and gadgets that work now came out that I'm a bit curious about. I think everyone who's looked into the topic at least a little bit finds all of these memes and the issues with, well, machine learning is just statistics, it's just nothing else, just a mask with a cooler name, but the basic is statistics. What would you say is there a difference, and if yes, what is really the qualitative difference between machine learning in itself and just statistics?
Yeah, they're very, very similar. I've taught courses, and I teach courses in statistics, but I've taught courses in the machine learning department. And I often start one of these classes and trying to explain the similarities and differences. And one of the jokes I usually make is, if I'm teaching in Baker Hall, which is where the statistics department is, I call it statistics. And if I'm teaching in Gates Hall, which is where the machine learning department is, I call it machine learning. But but there are, I think that there are differences in focus. I think machine learning tends to focus a lot on the task of prediction. Like, here's an email, can you predict whether it's a spam or a real email, that kind of thing. And and also the focus in a lot of machine learning, of course, is in scaling things up, making them work on really big problems. Whereas statistics, I would say, views prediction as one task within a bigger set of tasks. And although we do work with large problems, sometimes it's not as large a focus as it is in machine learning. But they're both about analyzing data ultimately. So in that sense, there's a huge overlap between the two.
Really interesting. That's like, because for me, I personally am curious. I talk about with many business owners, with many people who have companies, and with many normal people every day, Joe, Schmo, and just normal jobs, and they just don't really quite understand what the AI, as it is called today, is, because we're not at the general AI level at all. They're like ChatGPT, you get a text, but the AI does not really understand or consider what it is saying, as far as I understand it. It's just a statistical calculation of what is the most likely next word that should be done as the next one to the query that exists. And I've got like a database of, let's just say, 1 million texts, and then it checks, okay, usually if these combinations of words or characters are used, then it's most likely that these characters and combinations are supposed to follow that. Is that in the basis somewhat correct, or am I completely misunderstanding what is going on?
Oh, that's correct. When we think of AI these days, we're thinking of just ChatGPT or DALL-E or something like that. It of course is doing a complicated version of what you said, but that's what it's doing. It's really just estimating a probability distribution, say, on the set of sentences, and saying, given that I've seen these sentences, what is the likely set of sentences that should follow? And it's doing this on a scale that's hard to imagine, with the size of the data sets and the amount of computing that goes into actually fitting the models and so on. So I don't want to trivialize that, because it's the engineering there is very impressive and very difficult. But it is just a very large statistical model. That's basically what it is. And it works surprisingly well.
Awesome, crazy. It's wow that this field has led to such a result. To me, it's magical. And as you said, the engineering feeds behind it, because many people, they just know the typing it in and they get a result, but there's so much hardware behind it. There's so much optimization of code to make it work as good as possible. Like, if you have these things, these queries and loops and stuff that is going through millions or billions of data points, there is a huge importance in being efficient in the code and in the formula with which it calculates. And that's crazy to me. Could you help us a bit look behind the veil here? What are some challenges that we as normal people might at least understand with your help of layman's terms? What are the challenges?
Yeah, well, first of all, just to be clear, I'm not an expert on those kinds of models, but what, these are usually called deep learning models, which are, you can just think of as models with many layers to them. And the important thing is that they have these parameters that are estimated from data. But these models, so a typical statistical model might have 4, 5, 10 parameters, whereas these models have billions of parameters. And so you have to figure out, well, what are good settings for these parameters? And that's the training process. And that's where you take the data, which could be, like everything on the internet, for example, and you're trying to estimate what are good values of these parameters. If you described this to someone 20 years ago, you'd say, well, there's just no way you're going to do that. There's just too many parameters to estimate. But of course, they've shown that intuition is wrong. And so there is just a lot of very clever optimization going on to find good settings for these parameters so that these models will work well. So this process, which is called training the model, which is estimating the parameters from the data, just involves very, very smart optimization techniques, but also just lots of computing. I mean, you just have to have very powerful computers to be able to do this.
It's crazy how much computing power and chips, and with the GPUs they mainly work now. It's crazy. But I think your work in general is also maybe not directly in that field, but very directly in that field in another way, because you've helped understand. Now, let me read it so I don't make it wrong. The non-parametric inference in simple terms. It's like, if I understood it correctly, it's a way to how approach different methods compared to traditional statistics to get easier results, like how to work with complex data to get specific meaning out of it, if I understood it correctly.
Yeah, I mean, so just to give you,
if I just may ask for the viewers here, what is the difference in statistics between data and complex data? Like, where is there the beginning? In just a little short overview, please.
Yeah, so let's make a simple example. So suppose I measure the blood pressure of a bunch of people, and I want to, from that, predict some other health measure, like some blood measurement. And you can picture that as just simple plot, where on the x-axis I have blood pressure, and the y-axis I have some other health measurement, and then I just have this scatter plot. And you want to be able to describe that trend, that relationship, and the simplest way to do it is to put like a line through the data, and that's called a linear regression. And that's a very, very simple model going back hundreds of years, but it works surprisingly well in a lot of problems. If the data look very nonlinear, if it doesn't follow a nice linear trend, then that simple method is not going to work. And that's when we use what you've alluded to there, called non-parametric inference, which just means we're not restricting ourselves to simple functional relationships. We're going to allow very complicated relationships between the two things. But then data can get far more complicated. Now imagine I'm trying to predict whether you're going to get a certain disease based on measuring thousands of your genes. And so now all of a sudden there's thousands of variables. There might be more variables than there are subjects in a study. And now you're into this realm of very complex data, and we have to use much more complicated techniques.
And you developed one of the methods that makes this easier or possible, huh? Do you understand it correctly?
I did. I mean, I've developed.
Researched it. I mean,
Yeah, I wouldn't say I don't. Yeah, yeah. I've done a lot of research on the techniques. So what ends up happening is, typically, is people will come up with techniques for analyzing data, often very, very done very heuristically or intuitively. And then you want to say, well, what are the mathematical properties of these techniques? When are they reliable? And that's the kind of a lot of the work I've done is to develop the properties of these methods. Now and then, someone will come up with a brand new method that turns out to be, surprisingly successful, and it can be field changing. I don't think I've ever done that myself. A good example, just to give you an example of this, is my friend Rob Tibshirani, who's a statistician at Stanford. One day came up with this method he called the lasso, which is a way of doing relating some outcome like a disease or some measurement to very large numbers of variables. There's thousands of variables, like genes, for example. And this was a difficult thing to do. And then he came up with a method which you can implement very easily and quickly and works very, very well. And so that's kind of a field-changing discovery that they don't happen very often, but now and then somebody will come up with something like that. I've been more about studying methods and figuring out their properties.
Interesting question. It's like he finds out new stuff. Is it like just finding a formula, how to use it, or what? How can I imagine it? What would you say to layman is like, how do you find something new in these fields? How does that work?
It's usually through necessity. So let's go with this gene example again. Say I want to say which genes predict whether somebody gets Alzheimer's disease or not. And so I might have 1,000 people in a study. I might have 500 people without Alzheimer's and 500 with, and I've measured thousands and thousands of genes on these people and how strongly expressed are these genes. How can I predict the outcome here, disease or not disease, based on these thousands of genes? There's so many parameters there that I have to estimate. And the idea there was that the Rob Tibshirani came up with was the notion of sparsity, that we might measure thousands and thousands of genes, but really maybe only a small number of them are involved in the disease, and the rest of the genes really have nothing to do with this, or at least they're not very predictive of this. And so we really want a model that's sparse, that really somehow figures out that you really only need to worry about a small number of genes. He expressed that as a mathematical optimization problem, and that problem had the problem that he wrote down had a certain property known as convexity, which is just a nice mathematical property. Convexity is kind of a dividing line in the world of optimization, that things that are satisfy this property of convexity turn out to be things that you can often solve very quickly, and things that are non-convex are very hard to solve. And he came up with this optimization problem, which was convex, and so you can solve it very quickly, and it leads to a way of doing prediction that's very fast and very often quite accurate.
It's cool. So, okay. So convexity means like how closely and how easily it is connected and has to do with the result. Am I understanding that correctly?
Well, it has to do, in some sense, you might say, with the shape of the problem. So if I were to draw a curve like this, that's a convex function. Whereas if I drew a curve that looked like this, that's a non-convex function. And it's a little bit harder to picture these things because we're really dealing with things in high dimensions. But this convexity just makes most problems easier, both to study mathematically and to implement computationally. I mean, people in AI especially have made incredible progress dealing with non-convex problems, surprisingly. That's one of the things that's been really making a lot of these AI things work, is that they have found ways of optimizing things that are very non-convex. But whenever possible, we always try and hope to express something as a convex problem, just because it makes it easier.
Okay, cool. Good. You mentioned the AI guys again, and I want to ask something like, how much is it that we found new solutions, and how much is it, okay, we're just throwing more and more and more computational powers at the same problems? It's like, can we imagine, okay, we get much further? Is it more, oh, you just need to build a server farm that's 5 times as big and you'll have general AI? Or is it, no, we need something in the foundational, as you said, in the formula or in the method to change to get to that level?
I think it's a combination. I think they go hand in hand. And people keep throwing more and more computing at things and more data at things, which makes things faster and better. But then along the way, people keep having more ideas too. And so I think this kind of development of ideas and throwing more computing at it goes back and forth constantly. And I really think it's the combination of those sort of combination of innovation and computing power go together to keep making better and better systems.
If you're okay, we talked about a bit about the technicalities and the objective stuff. I would like to ask a few things more on the philosophical meta level to know what, if you're okay with that. I would like
Sure.
to know your opinion about AI. Some people are afraid we're gonna lose the jobs, it's gonna be Terminator-like, we're gonna get screwed over. Others say it will be more like Star Trek, utopian, everybody will have everything with the machine that solves all the problems, and then we've got robots and androids, and it will be awesome for us all. Some other think, oh no, it's gonna be technocracy with just Zuckerberg owning us all and Google, and that's it. So where is your take? What is your hope, fear, realistic opinion? What do you think what it's going to be like?
Yeah, so I can just give you my subjective opinion about this. I think that there's obviously always concern for the problems can arise. That's true for every technology, but I think a lot of the fears are frankly overblown. I think every time there's a new technology, people freak out. You know, when it used to be something like 90 or 95% of the people in the country used to work on farms, and then we invented tractors and other machines, and now only a tiny percentage of people work on farms, but it's not like we have 95% unemployment. People find other things to do. Yeah. And so I think it's going to be a similar thing. I think some jobs may disappear or get radically changed, but we'll think of other jobs. You know, I think the one maybe scarier part of it is the speed of the change, you know, and the fact that, frankly, I think when these models get incredibly complicated, maybe nobody really understands them in some sense, that we get this emergent behavior from these systems that nobody expected. But ultimately, you know, I don't know, I feel like humans are adaptable, and I feel like we're just going to adapt to it. And you know, I just think a lot of the doomsday scenarios are sort of unlikely. But you know, again, I'm not an expert in that area, and I'm not, you know, I'm not a philosopher and so on. So I'm just giving you my, you know, gut feeling about it. But my feeling is I'm not worried about it.
I think that's a good. I'm gonna be honest, I'm on the same team as you. I mean, yeah, of course, there's political implications, there's economic implications. It's not going to be great for every single individual in the world, of course not. Like, as you said, but I remember in marketing, for example, it was the same. Oh, then Facebook came and the internet came, and suddenly we will never need printed stuff again, and nobody's going to read books and so on. And then how many people are now in SEO, search engine optimization, or Facebook ads channels, or Google ads agencies, and that didn't exist 20 years ago. So there is a switch and a shift to other jobs and other takes. So I think, as you say, we're not going to be suddenly completely 95% unemployment rate, as you said.
Yeah, yeah, I'm on the same page. Yeah.
And just out of curiosity, I recently stumbled upon a thought experiment, a little philosophical questions for a general AI. If you consider that it will most likely be connected to the internet and can get all of the information it will get, and that one of our humans' theories is the simulation theory, that all of us just exist in a simulation, like in the Matrix, let's say.
Yeah.
How the AI would have to consider that it might be not in the real world, but just in a sandbox environment for other human scientists to check it if it's going to be good or bad. And so it will never allow itself to become really bad, because it would have to fear that it gets shut off. Have you heard of that before?
I haven't heard of that, particular one, I know, of course, about the simulation
Yeah.
hypothesis that we're all just living in a simulation. But yeah, there's many different versions of these things, and I guess nowadays you can think of even more and more exotic versions of these things.
Kind of crazy, but because it was suddenly, true. If it goes rogue, it has a non-zero possibility that it will just get shut off and can never do anything against it. So for its own self, what's the word? For it to keep
Preservation.
on existing, sustainable, the best options it has is to be good to humans. And I thought that's a nice thought experiment a bit.
Yeah, that's an interesting one. Yeah.
Now, what would you say for younger generation? Because I always like to talk a bit about career options, about future, about life. Is that field still one where you think, oh, it's good to go into it? You can make a career, you can have a good life, and there are economic implications that is going to be worthwhile? Or do you think statistics is more of a field that's already a bit overcrowded and you better go into another field? What's your opinion for the younger ones that watch this channel?
I think, my guess is statistics is going to be around for a long time. We're at, we've always had, for example, as far as I know, like close to 100% employment. Every graduate from our programs never had a problem getting a job,
Wow,
as far as I know. And
that's a number. Wow.
yeah, there's always going to be demand, I think, for people who develop methods for it, for dealing with data. It's just, if anything, I think it's a bigger and bigger part of the world. It's going to change, but the tasks that you'd want somebody with a statistics degree to do might be different. And as time changes, and certainly they're much different now than they were, some years ago. But if I had to predict, to me, it seems like there's always going to be a need for people who are experts in understanding how to analyze and think about data.
Okay, that sounds cool. That's very, very optimistic. That's cool. That's nice to hear. That's really great. And now about your study and work a bit. What are you working on right now? What are the challenges that you face that you're going heads on, or are you just more laid back right now and say, no, I'm just what can we expect of you, or what are you doing right now?
Yeah, I still do what I did originally in some sense, which is to always have some projects going about statistical theory and some applied things. On the applied side,
Yeah.
I've been pretty lucky to be working. We have a group called STAMPS at CMU, which is Statistical Methods for Physical Sciences, and I'm happy to be part of that. And I've been lucky to work with over the years astronomers, and right now I'm working with some particle physicists. So I see that continuing, and I'm part of we have a group here called Delphi, which is an epidemic prediction group that's run by some colleagues in machine learning. And well, of course, we were quite busy during the pandemic, as you might guess.
Yeah,
And
wow.
yeah, so I'm still part of that group. And then I have some theoretical projects going about various aspects of statistical theory. So I just imagine I'll just keep doing those things.
Cool. Now I'm a bit curious. I gotta ask about Delphi project. Like, was it, and I don't want to sound cynical, but like, was it a good thing for the data to have in the modern age another pandemic to like see data points, or was it more of a positive for the field just from the data standpoint and the methods? I mean, not from a human level, or was it a negative in the sense of, okay, we don't know enough and our methods are not correct? What was it like?
It's a mixture. It really is. Epidemic data are very difficult to deal with. That's one thing I learned. So before the pandemic, this group, which and let me just say that the group was started by my colleagues Roni Rosenfeld in machine learning, and Ryan Tibshirani, who statistician, used to be a colleague of mine here, since moved to Berkeley. And it was a very small group. There was a few of us, few faculty, a few students, a few postdocs. Then the pandemic, and the by the way, the focus was usually on flu prediction.
Yeah.
and Roni Rosenfeld had developed quite a strong relationship with the CDC. But of course, when the pandemic hit, they said, "Hey guys, you got to switch over to COVID forecasting," and it was a sort of emergency status. And Roni and Ryan built up the group into a very large group, maybe 60 people at one point, 70 people. And you know, they Facebook and Google and various places, CDC were very generous about giving funding. Google lent us like a whole bunch of engineers for 6 months. It became a very big enterprise. It's still very big. But one thing we learned was how hard it is to predict a pandemic, and especially because the quality of the data was not very good.
Okay.
And of course, things are just constantly changing, and people's responses are constantly changing. So I think we learned a lot about that's the good news is I think we learned a lot.
Yeah.
And the Delphi, if you look at the Delphi website, for example, it's very sophisticated now, and there's a lot of information there. But it does worry me that how difficult it is, because it means that if there's another pandemic, and I guess there will be eventually, you know, it maybe we'll be better at it the next time around. But it's hard. I mean, the data are not the greatest data in the world, and
May I ask there? And as I said before, if issue with the question, no problem. I'm just curious. You say the quality of the data wasn't that good. I imagine with our modern society, shouldn't like hospitals know how many patients they have? You know, where are the people? Who is when at which area traveled with whom and so on. Shouldn't that be quite good data?
yeah, but every hospital had different reporting habits, and different states had different reporting habits, and of course people had their hands full, you know, with
Yeah.
with
Wow.
with sickness, and so reporting the data wasn't necessarily their top priority. And so you would get days when you were getting reports of 0 deaths, and then all of a sudden you get this report of a huge number of deaths because they hadn't bothered to upload the data from a few days before, and you know, different
Really?
states were reporting things differently, and so it was quite chaotic. So I think, no, again, if it happens again, hopefully it'll be a little bit more organized. It certainly was better data than we would have had if the same thing had happened many years ago, because we just didn't have the technology for that kind of reporting. So in that sense, it was better than you would have expected. But you know, getting the data recorded accurately and reported accurately just wasn't a top priority for what was going on at the time.
It's interesting to hear about a little bit about the you know, behind the wheel what happened, because as a normal citizen you don't know any about that stuff, and
Yeah.
it sure sounds different than the typical how do the conspiracy theorists say that it was all orchestrated. It doesn't sound like oh, we had it all under control, every single detail.
Yeah, that's the problem with conspiracy theories, is they require this amazing amount of organization, and that just doesn't exist in the world. The world is a pretty chaotic place, and there's no mastermind behind it coordinating things.
Crazy. I didn't know, for example, that the hospitals don't have all. I thought there's like a standard for, okay, people are sick. This is the 30 variables that you give in for a patient or something like that. Didn't know that it was that different from hospital to hospital. I thought it was a national way of getting the data. Wow.
Well,
Interesting.
there probably are some standards. That end of it was not something I was specializing in, but for sure there was a lot of, you know, difficulties with the data. It wasn't easy data to deal with.
And you talked about another project that I'm a bit curious. I understand if you have any NDA or something, you don't need to talk about it, but I'm curious. Particle physics, also an awesome field for statistics. Well, what are you working on there, if I may ask?
Yeah. So there's a lot of data, you know, that physicists collect a lot of data, and they have a lot of statistical questions. And there's actually a group called Phi-Stat, which is physics and statistics, which is run by some a group of physicists that have regular meetings where very interesting meetings where there's a bunch of physicists and statisticians get together and talk about some of these problems. And yeah, there's a lot of different types of problems. One of the ones we worked on recently was something that I would call, I guess for lack of a better term, maybe it's a type of domain transfer where they had our colleagues in physics had a lot of data about a certain type of interaction that occurs in particle colliders, but they wanted to know what this would look like under a slightly different set of circumstances. So the problem there was to take a distribution, a collection of data basically under one type of situation, and then say, but under this other situation, what are the data going to look like? We need to know that in order to do the statistical analysis. And so a group of us worked together to develop some statistical techniques to do this kind of, as I say, I guess I would call it domain transfer. So that's an example of the kind of thing that we might be involved in.
I mean, sorry if I'm a bit like a little child, but I think that's so cool. It's like on the frontier of human knowledge, wisdom, so much stuff where it's like we're getting a step further and further as mankind, as a whole, and you're like straight in the middle. You're one of those guys who are the pioneers who get asked the stuff, who get to look at all of this things. I really think that's cool. I
Well,
really think it's impressive too, in all honesty.
No, that is one of the great things about being a statistician is you can work with particle physicists, you can work with biologists, you can work with medical researchers, you can work with anybody in any field. If they have data, they want, statistical help. And so the nice thing about the field of statistics is you really get to work in lots of different, with lots of different interesting people in different fields.
What would be we're almost at the end now, just a little question. What do you think personally is what are you most curious about in research right now? Like not what you have to work on, but like in general, as a human, where you think, oh, that's an interesting field, like more the Neuralink from Musk or more space exploration, or do you think, oh, no, we've got here on Earth enough other things to learn, biology, or maybe something completely different, like philosophy? Who knows? What do you think is one of the most interesting research fields?
Actually, I do think it's AI. I think that the emergent properties of these systems, like that ChatGPT can maybe solve math problems or do things that it wasn't specifically programmed to do, is a really fascinating thing. And I think we're just seeing the beginning of it. This is just the tip of the iceberg. So I think it's going to be really, really exciting to see 5 years from now what's happening in AI.
Any idea, what would you say the time frame for something like a really general AI, super intelligence? Do you think still too early to say?
Yeah, I think
Or
these
never?
things. Well, no, I think I think it will happen, but it's just so hard to predict. I mean, people can make predictions about these things, but as a statistician, I would say most predictions are bad. And I just think no one really has any idea. It could happen next week. It could be 100 years from now. I don't think anybody really can guess what how long this is going to take.
And now that I've got you here and you're a statistician, just one question. I know it's not your field, and of course, all of these companies have their own codes and they won't let just anyone look into it. But like, do you have a general grasp and understanding of why does it happen that an AI or machine learning or deep learning is constructed to do one thing, but it suddenly does something completely different? And how does that happen?
That's the $1 million question, I think. It's sort of ironic that these systems have been built to be more and more complex with more and more parameters because that's what makes them work well. But the implication of that is it leads to behavior that you didn't expect. And I think trying to understand that is one of the frontiers. There's a real push for what people call explainable AI, which is that, you want to build a system not only that can make these amazing predictions and do these amazing things, but then so you can say, yes, but how can we understand what it did and why it did this? And so now I think this thing, which is called explainable AI, is a pretty major research area that people are interested in, precisely to try to answer that question.
Wow. So it's really that much that the people who did it don't know why the thing the model does the result. I thought, okay, it's like surprising, but when you look at it, you can analyze it and realize afterwards, okay, now we know why it got that result and why it is saying this. It's not that easy to even know
Not
why.
that easy, and that's a research area. That's what people are trying to do, is to try to create systems that can not only do things but then explain why they did it.
That's very interesting. That's very, very, very interesting. Professor Wasserman, I know your time. I've got still so much I could talk with you and ask about, but I know your time is valuable. I thank you very much for the time you took answering these questions, helping us all understand a bit more about statistics, about machine learning and AI, how these things are intertwined and a web, and how we as normal people interact with these things every day without maybe consciously knowing it. But thank you very, very much for your precious time. Thank you.
Thank you. My pleasure.